Nanotechnology, making small stuff do big things. Pretty simple definition. Our institute at Rice has a rather small vision to solve the world's most pressing problems through applications of nanotechnology. So obviously I'm a technical optimist. Our namesake, Professor Richard Smalley, shown here, is famous for the discovery of the buckyball, also known in some countries as the soccer ball. It's actually a carbon-60 molecule, or Buckminster fullerene, so proving that scientists do have a sense of humor. That's the official name of the molecule, also known as a buckyball. It's about a nanometer in diameter, which means it's about the size of 10 hydrogen atoms. And it was a remarkable discovery that puzzled and horrified the chemistry community. And it took at least 5 years of hard work on Professor Smalley and Curl and Croto's part to defend it against the critics. But eventually, in 10 years after that, they won the Nobel Prize, therefore validating this as one of the first discoveries that started the field of nanotechnology. So I did work for the federal government for 37 years, and everyone here knows that the federal government gets it just right. This is the official definition of nanotechnology, and you can read through it at your leisure. It's rather complicated, but it has to do with things that are about 1 to 100 nanometers in diameter. So the international community is a little wiser. They've gotten a smaller definition having to do with applying scientific knowledge to controlling and using matter at the nanoscale where size-dependent properties occur. The best definition came out of one of our entrepreneur workshops about 8 years ago. Anything is nanotechnology that under the name of nanotechnology makes money. So this is a great audience, but you're not as tough as the audience that I had to give this new definition for nanotechnology to about 1.5 years ago. And I went to the Ig Nobel Prize ceremony. This is the ceremony that recognizes the worst stuff that's happened in the last year. And they invite 4 specialists every year to come give a 24/7 lecture. So don't worry, it's not 24 hours, 7 days a week. It's a 24-second lecture on the subject, followed by a 7-word definition that your grandmother can understand. And about an hour before the event, I finally came up with the definition, making small stuff do big things. In case you're interested, the guy on the upper left there with the V chip, that's a lawyer from New York that's standing by in case you get obscene in your discussion. And the guy on the right here is the referee who will cut you off sharply at 24 seconds if you go over. So that's a tough audience. I realized I needed to add a few more words to make it a true technology, so later I decided we need to add, and selling them. Okay, how big is a nanometer? Well, those of you who have enough hair that you can spare plucking one, feel how thick it is. That's about 100,000 nanometers thick. So when you start working at the nanoscale, you're working way, 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 way below where you can actually see or feel things. So this is really about the science of the small. So this is the technical slide for today. There will be a test on this as you leave, so pay attention. First of all, the size-dependent properties. What's that all about? Well, it turns out that if you take materials and start looking at them when they're sized in the nanometer range, their properties indeed do change. And scientists didn't know this before until we started having the tools to actually do this. So most of you probably have a gold ring on or something gold, and you know what the properties of gold are. If you start chopping that up into nanometer-sized pieces, as you get smaller and smaller, you eventually run through an interesting phenomena that the color changes. And in fact, you can make different sizes of gold particles that go through the entire rainbow of color. And I'll show you in just a minute how you can cure cancer with that. Now, the other thing that's neat is if you start chopping up something and making very small pieces out of it, you start realizing that there's a heck of a large number of those little pieces. So we're just about finished with the basketball season. So take a basketball-sized piece of gold, there's one particle. It's got a surface area of about 0.2 of a meter squared, not very big. And as you cut that into smaller and smaller particles, when you get down to maybe 25 nanometers diameter, you have 870 quintillion particles. That's 1 followed by 18 zeros. And the surface area of all those particles combined is equal to about 4,000 basketball courts. That means if you're going to do something like make it a very precise sensor, or you're going to make a catalyst that will help us refine oil or something like that, if you nanosize it, you're going to get a lot more power out of doing that. And lastly, there's quantum effects that take place when you get down that size, but we're not even going to talk about quantum mechanics today. So, how does this work for curing cancer? Now, my colleague Mauro Ferrari couldn't make it today, so I threw out some of my other slides, and I threw in several slides to talk about how size-dependent properties are going to help us in the nanomedicine field. And I have to say that Rick Smalley had two great visions for nanotechnology before he passed away in 2005. The first was nanomedicine. Unfortunately, we didn't get there fast enough to save him from lymphoma. But the second was nanoenergy, and that's what I'm primarily going to talk about today. But before we get there, I'll tell you a little bit about gold nanoshells. So Professor Naomi Hallis, electrical engineer, and Professor Jennifer West, bioengineer, about a decade ago came up with the idea of taking a particle of sand that's maybe 40, 50, 60 nanometers in size, coating it with nano gold particles until you get a solid coating. And that gives you a dielectric core and a metal shell. And they discovered as you change the size of that or change the thickness, you can drive the wavelength of absorption or scattering all over the visible into the infrared, shown here for the technical geeks in the audience. And that allows you to actually do something very special. So the infrared is very cool. This is a visible laser. Everybody can see it's green. If I hold it up to my finger, you see the green light doesn't go through my finger. But if I take out a red laser, voila, you can almost see that. You can see that the red goes clear through tissue. And everybody who's ever lit up their hand with a flashlight as a kid in a tent behind the house at night understands that. So if you use an infrared laser that can go maybe 3 inches deep through tissue, and you have a gold nanoshell that is designed to exactly absorb that radiation very efficiently, you could actually use it to heat up a cancer cell. So here's the way it works. You got nanoshells absorbing in the IR. You've got a target cancer cell here. You can attach a biological marker that specializes in the cancer cell, but it actually works almost as well even if you don't do that. So you then, let's go one more, inject it into the bloodstream. It flows through your body. It accumulates in tumors, but anywhere it finds a cancer cell it's going to attach to. You shine an infrared light over the whole body slowly or target the cancer area. It heats it up about 10 degrees C, kills the cancer, and you're done. Very cool. Now the problem is in the animal studies we did, it was a financial nightmare because nobody planned for the animals to survive that long, so it was an accountant's, well, okay. Yeah. So here's what it looks like. Here's the hind section of a mouse. Everybody recognizes that, of course. There are two breast cancers that have been planted in the mouse, and they're growing here. An infrared laser beam is shining through, heating up only the areas where the cancers are and killing the cancers. So in animal trials, it looked like this. You had the sham group and the control groups here. They all died within a month. The treated groups in every animal study that was done were 100% effective in killing the tumors. So we are now in third phase. We're in third phase clinical trials at MD Anderson and in San Antonio for patients with neck cancer and prostate cancer. And as soon as we get through the 2 years of study of that, if it works as well as the phase 2 showed, this is going to be a new powerful weapon in the war against cancer. And this has potential for use in at least 40 different cancers, can even be used deep in the body by putting a catheter in and shining the infrared light inside. So that is a short summary of Mauro Ferrari's talk, except this is only one of maybe 200 different areas that nanotechnology is being used to revolutionize medicine. And in the next decade, you're going to see amazing, amazing new diagnostics and treatments come out of nanotechnology. So let's jump to energy in the last half of this talk. So when Rick Smalley and I got together in 2002 and started talking about what we should be doing with the Institute, he went out and started giving talks, and then I went out and started giving some talks, and we would ask an audience like this with a blank slide, nothing in the numbers, what do you think the most important problems facing humanity for the next 50 years are going to be? And people would shout out answers. No audience ever shouted out energy in the top 5. But we tabulated them all, and after about 10 audiences, we chalked them up, and then Rick did something very clever. So instead of leaving energy at, say, number 5 or 6, he put it at the top and said, let's invoke a miracle. Suppose we have all the energy we need, it's widespread available, it's environmentally clean, and it's cheap. Can we solve the other problems on the list? So let's take a look. How about water? Well, here's the globe. Notice anything? The world's got a lot of water, but it's got 2 problems. It's salty and it's not where you need it to be. And to solve either of those problems takes an enormous amount of energy. How about food? Well, first, seed number 2, and secondly, you start transporting food around and so forth, fertilizing, a tremendous amount of energy used in food. The environment, arguably a lot of our troubles come from the kind of energy we consume, the way we consume it. Poverty can be defined as a lack of access to energy. Terrorism and war, now I don't know, have we ever fought a war over energy lately? I'm trying to think. Disease, a lot caused by bad water. Education, I can hear the stomachs growling. You can't learn on an empty stomach, et cetera, et cetera. So we may not solve all of these pressing problems facing humanity, but if we don't solve the energy problem, it's going to be really, really hard to tackle all these other problems. Is there any other factor you could put at the top of the list and have the same result? There is one. Population. Suppose we put population up at number 1, and then a different miracle happens, and all of a sudden there's only 1 billion people on the earth. Most of our problems go away. The earth can easily sustain 1 billion people, but it's having a lot of trouble sustaining 6.8 billion people, or maybe 9 or 10 billion people as we move through this century. So this told us that the most pressing problem facing humanity is energy, and that nanotechnology needs to get off its tail and start working hard on solving the energy problem. So that's what we did. So one of the things that Rick Smalley did in his genius is to take a look at the problem in 2003. We consume about 15 terawatts of energy. That's about 210 million barrels of oil equivalent per day on Earth, total. About 85% fossil fuel, a little bit of fission, a little bit of biomass, a little bit of hydroelectric, almost no solar, wind, geothermal. That's the way we are today. That's the way we got rich and prosperous and spread it around the world in the last century. What's going to happen in this century? By 2050, estimates are that we're going to need between 30 and 60 terawatts of energy. So you heard the wind energy discussion. A terawatt is 1,000 gigawatts. So when we talk about achieving a gigawatt of renewables, we got to do that 1,000 times to get a terawatt. And if we need 15 more terawatts or 45 more terawatts, this is a huge problem. This is the terawatt challenge. Now, we'll still have oil and coal and gas in the next 50 years, but it's going to be a decreasing part of the mixture. Fission and fusion may get bigger. Biomass certainly is going to get bigger. A different miracle has to happen. Renewables have to come up to 50% of our energy use by 2050. How is that going to happen? Well, you've heard a lot of discussion, well, not a lot, but some discussion about the energy problems today. Nanotechnology is behind a lot of the things. And the way we use energy today is horrendous. Look at this boat. 1, 2, 3, 4, 5, 6, 7, 8 250s on this sucker. Okay, it is a drug runner's boat, so. But wouldn't that be a great fishing boat for the Gulf to go out and get the big tuna, huh? And here's the way a lot of the rest of the world thinks of energy, right? So here's your challenge. Which of these last 2 ideas is most harmful to the environment? Okay, we got to figure that one out. So here is the sad look at our total energy picture for up through 2100. So here's oil, and here's natural gas, and here's coal, and here's the population growing, and here's the total energy being consumed, and here we are about 2010 right here. And as we go toward 2100, if we hit 10 billion people, if we don't consume more energy by industrializing and bringing the standard of living up worldwide, that's about where we'll hit. The trouble is that's very conservative. The reality is, if the world actually gets more economically developed, and certainly China and India are headed that way rapidly, then here's what the curve is more likely to look like. And this yellow band in here is the gap that has to be filled as we run out of easily affordable fossil fuels. So that's why when I was in the Air Force, the first time every time we captured an alien, we asked the first question is, do you have oil and can we get it? Now my wife found the answer in one of the tabloids in Houston here, that the real reason Bush went to the moon, wants to go to the moon, was that there's oil on the moon. Well, don't believe everything you read in the papers, okay? So here's an eye chart for you just to tell you that the nanotechnology community and the energy communities have now woken up about the idea of nanotechnology impacting energy. And a lot of the advantages and the new developments that are coming in renewable energy are coming out of nanotechnology. Now the people that put this chart together put only fossil fuels right here. And in Houston we're spending a lot of effort, and the oil companies have also awakened to the ability of nanotechnology to go downhole and help find more oil and get more oil out. So nanotechnology is going to be the way that a lot of our energy improvements happen over the next 50 years. So here's another summary of what situation we're facing. Here's the yearly energy consumption on Earth. Here's the amount of oil, gas, and coal we have available. Here's the hydropower, geothermal, biomass, wind energy, and here's what we get from the sun. So we get more energy from the sun in an hour than the entire human race consumes in a year. So obviously the long-term answer has to be solar, and that's where we need to place a lot of emphasis in order to get through this, making this miracle occur. Well, we could do it with today's technology. We saw earlier that if you cover up where I grew up in the panhandle of Texas, with today's solar cells, you could generate 3 terawatts of energy. That's enough for the United States. If you cover up the bad part of Texas, anything north of Houston, all of Oklahoma, Kansas, Colorado, New Mexico, so now we're getting into blue state, red state arguments, right? With today's technology, we could provide all the energy that we need on Earth. Just cover up that much of the Earth's surface, and we've got it covered. So let's think about using the small squares and putting them in all the different continents and spread it out so everybody pays a little bit of land area, and we've got all the energy we need with solar today. But solar has a couple problems, the biggest one of which is night. And the second problem is that the best solar is not where the most people live. So Rick Smalley walked into the office one day and said, here's my answer for the next century. The distributed storage generation grid. Let's stop thinking about transporting energy around as mass, i.e. oil and coal and gas, with all of the huge, probably $20 trillion infrastructure to do that. And let's start working toward an infrastructure where we transmit energy around the world as electrons. Let's move to an electrical system. And to do that, we're going to need a better grid that can actually get the electrons where we want them to be. Let's think distributed. Let's think a solar panel on everybody's house. Let's think geothermal wells. Let's think every way we can get energy. And let's make it as distributed as possible. But let's not exclude the big guys from operating, because if we have a grid that's powerful enough to carry all this electricity around, we can convert our infrastructure over this century. And he called this, as I said, the distributed storage generation grid. And all we need to do it is nanotechnology. There's no other way to get the electricity in a grid wire to go over 12 time zones, which means you don't have to worry about storage. There's always sun somewhere on the earth if you can slosh electricity around the world. As Buckminster Fuller originally envisioned, in the background here, you can see Buckminster Fuller's worldwide grid concept from about 30 or 40 years ago. So, why nanotechnology? Because carbon nanotechnology, as discovered by Rick Smalley and perfected by and reinvented by a few other people over the last 2 decades, has given us the single wall carbon nanotube. Shown on the right side here, it's basically a piece of Texas chicken wire wrapped up into a cylinder, capped with half of a buckyball on each end, and it's a nanometer diameter. This nanotube, a single nanotube, will carry 20 to 50 microamps of current. And if you put trillions of them into a cable, and you can get even a fraction of that 20 to 50 microamps in the cable, then instead of a grid wire carrying 2,000 amps of electricity, they might carry 100,000 amps or 1,000,000 amps if we can figure out how to do that. And that's a research program that we're doing at Rice University, been working on it for a few years now, and we're at a critical stage of trying to figure out how this works. I skipped one point on the slide, that the strength of this nanotube, by the way, is the strongest material that we will ever have in the universe. So this is a very audacious statement. I'm glad I didn't make it first. It was Rick Smalley. And if he's right about it, then it's a signal for the engineers to get busy and start making stuff out of it. If he's wrong, it's a challenge for kids to figure out something better and invent it. So we're making what we call the armchair quantum wire. What needs to be done is go from single nanotubes to wires of nanotubes in large quantities. They all have to be the same type of nanotube. Mother Nature's made it hard for us, but we're getting closer to it. We're very close to a proof of concept on it. So this is a great vision. Without funding, it's just hallucination. Without hardware, it's just delusion. And the problem, as was pointed out by the last speaker, is that the funding for research and development in this country is going right down somewhere bad. Here's the space race. Here's the Apollo project back in the 60s and 70s. The blue is the age of medicine, which was the National Institutes of Health budget. And here we are today. And if we are entering into a new age of energy, then this little green marker here ought to be a lot bigger. If this is the most important problem facing humanity, why isn't the federal government really ramping up basic research in the area and companies jumping on the bandwagon to do development of the technologies? By the way, if it's the second age of space, this yellow bar, I also agree with her, needs to be very much bigger if we're ever going to make it to Mars. So here's the situation. Here we are today with easily accessible fossil fuel energy. Even if it's $4 a gallon, it's still relatively cheap, cheaper than coffee. Here's where our children are going to be operating. Here's where your grandchildren are going to be operating in terms of easily accessible fossil fuel. We've got to get going on this for these people on the chart. I don't want to be standing talking to my granddaughter about, how about you spend less time studying how my generation screwed up the environment and more time figuring out a magical solution. We know it's not a magical solution, though. It's a nanotechnology solution. What can you do about this? Well, I would say learn as much as you can about energy. Learn as much as you can about nanotechnology. And encourage kids to study science and engineering, and saving energy is just as useful as finding new energy. The more energy you save, the better off we are. I'm a numerator kind of guy. Yeah, that is a nanotexan, by the way. So the question is, will talking about energy and things like high-performance fibers, these same fibers that we'll rewire the grid with, are also potentially strong enough to build a space elevator? Or will talking about energy and lightweight conservation vehicles and so forth motivate kids into science and engineering, as it did for Rick Smalley and me? So here's Rick Smalley as a kid. Doesn't he look like a visionary? Yeah. This is me. I've just been a troublemaker. So I'll add a piece to the last speaker's talk by saying that in 1957, when I was a fifth grader, I read this book, Robert Heinlein, Have Space Suit Will Travel. I was looking at Sputnik and I said, I want to be an astronaut. I became a scientist instead. It worked out okay. So here's who I care about. This is my 2-year-old granddaughter about a year ago, class of 2030 at Rice, I think for sure. I know that's for sure, because here she is at age 13 months making buckyball models in my office. And when she finished, she said, "All done, Grandpa, what's next?" So just to show you that we're working on the continuation of this story, here she is now at age 2.5 with our now 6-week-old granddaughter, Bessie. And this is Millie and this is Bessie. This is the buckyball gal. So that's why I care about this problem for the future, not so much for me. So I'll end with Rick Smalley's mantra when we went through all this was, be a scientist, save the world. We are equal opportunity. Be an engineer, save the world works also. Thank you very much.
Thank you.